this presentation, we'll explore the research paper titled Fully Dynamic Connectivity in O log n square, Amortized Expected Time by Shen and Huang, and this paper presents a novel data structure for maintaining dynamic connectivity in graphs with near optimum amortized expected time complexity. And this is our group members listed below. This is the pre-defined schedule, and this is our work assignment. The content will be skipped, and you can overview it since we have already provided the slide and to cool. Okay. So for my part, I will begin with the introduction, and then we'll briefly describe the algorithm and also its complexity analysis. And this is the tentative outline. Okay. Let's get started. For the first chapter or the first section, we would like to introduce the concept of dynamic connectivity problem as a cornerstone of dynamic graph algorithm, and we will explore the intricacies of this problem and the contribution of this paper to its understanding through the Las Vegas randomized model. Okay, so the dynamic connectivity problem is a pivotal in the realm of dynamic graph algorithms. It revolves around efficiently managing a graph's connectivity through insertions and deletion of edges and determine if two vertices are connected. This problem is crucial across different computational models, showcasing its broad applicability. So there are three operations. So we can go at the heart of dynamic connectivity. There are three operations: insert, delete, and com, which stands for connectivity. Insert and delete modify the graph's edge set, while connectivity queries the connectivity status between any two vertices, a fundamental aspect of understanding graph dynamics. Dynamic connectivity has been tackled with both deterministic and randomized approaches, including Las Vegas and Monte Carlo models. A key strategy involves maintaining a spanning forest as a sparse certificate of connectivity, which is very crucial for answering the connectivity queries efficiently. Las Vegas algorithms are like a gambler in Las Vegas who plays until they win, ensuring that they always leave with a correct result, even if it takes an unpredictable amount of time. On the other hand, Monte Carlo algorithms are akin to a gambler who takes a calculated risk, accepting that there is a known chance of losing in exchange for a quicker gain. So Las Vegas algorithms are preferred when accuracy is non-negotiable, while Monte Carlo algorithms are chosen when speed is crucial and some degree of error is acceptable. Then we are going to introduce the algorithmic approaches here. There are two different approaches. The worst-case analysis is like preparing for the heaviest rainstorm when building a roof. It ensures that no matter how bad the weather gets, the roof won't leak. Amortized analysis, on the other hand, is like budgeting for monthly expenses. Well, some months might be more expensive due to one-off cost. The average cost over the year is manageable. Worst case analysis is crucial for systems where failure to perform in a timely manner is not an option, while amortized analysis gives a more balanced view of performance, particularly when an algorithm experience operations of varying cost. The nature of a spanning forest, whether public or private, significantly influences the algorithm's behavior. A public forest allows operation sequence to adapt based on the forest structure, while a private forest ensures operation sequences are selected without prior knowledge of the forest state. We are diving into the fascinating world of dynamic connectivity algorithms. The algorithms play a crucial role in understanding how components within a graph are connected, as edges are added or removed, which correspond to the insert and delete in the previous three operations we introduced. A key concept contained in the previous slide is the use of a spanning forest denoted as F. This forest acts as a sparse certificate of connectivity, meaning it is a minimal subset that still fully represents the connectivity of the entire graph. It's essential for efficiently answering whether any two vertices in the graph are connected. Let's explore an important distinction in how these algorithms can be implemented. The visibility of a spanning forest, which can be either public or private. When a spanning forest is public, the sequence of operations on the graph, specifically insertions and deletions of edges, can be influenced by the current structure of F. This is because if the forest is visible, decisions about which edges to manipulate can depend on the forest state and even on random choices made by the algorithm in the past. On the other hand, when the spanning forest is kept private, the sequence of insertion and deletions is selected without any knowledge of F's structure. This approach, known as selecting operations, obliviously ensures that the update to the graph unbiased by the current state of connectivity. Sorry, I just skipped one slide and we continue this slide, sorry. So the visibility of the spanning forest has significant implications. With a public spanning forest, there's a risk that the sequence of graph operations could become biased. This bias could be exploited by adversaries who have access to the forest structure. It introduces a layer of unpredictability and potential vulnerability in how the graph evolves over time. Conversely, maintaining the spanning forest as private guards against these risks. It ensures that each operation on the graph is chosen independently of the forest state, preserving the integrity of the algorithm's performance guarantees. This approach upholds the theoretical foundations of dynamic connectivity algorithms, ensuring their reliability and effectiveness in managing graph connectivity. Let's talk about the contribution of this paper. In our discussion today, we will be examining the groundbreaking result, maybe not groundbreaking, but very advanced result presented in this paper, where the authors have proven near optimum bounds on the amortized complexity of dynamic connectivity. This is within the context of the Las Vegas randomized model, which is known for its probabilistic guarantees of success. A key aspect of their approach is the use of a public connectivity witness, which is, in the case, a public spanning forest. This witness is crucial for verifying the connectivity status within the graph as it evolves over time. And in this section, we will stop at theory 1.1. The authors present a theory that is a testament to the efficiency of their dynamic connectivity data structure. The structure is capable of supporting the insertion and deletion of edges. Sorry. Let's stop here and we will continue in the next video.